watch our friends, subscribe to our channel and click the bell icon for the latest update. Today we're going to start with your chemistry for the class 12th, and that is your class 18. We have to start discussing about it. In the last 17 classes we had discussed about unit 1, unit 2, unit 3, unit 4, unit 5 and unit 6, which we have to start with unit 7 here. That is the P block elements that we have to cover up here, and that is also an important one as well. In the P block element that you have to consider about it, how you have to figure it out, all these. And in the same cases, before starting with this, it's a huge request from my side to all the viewers to please go through the subscribe button and please like, share and subscribe our channel so that many maximum people can get the information at once, and even though you can also enjoy the video as well. And the same cases here that we talk about it, and which is in terms of the P block elements, and we start with it. In P block element, the diversity in the chemistry is a hallmark of P block element that manifested in their ability to react with the elements of S, D, F blocks as well as their own. In class 11th, we have learned that the P block elements are placed in group 13 to 18 of the periodic table, where their valence shells electronic configuration is NS2 and P, that is 1 minus 6 till from 1 6 here that we have. So just write it down for the electronic configuration for this. Which is equals to NS2 NP from 1 to 6, and that is except helium, that is we have 1s2 configuration. The properties of a P block element, like that of the others, that are greatly influenced by atomic sizes, ionization enthalpy, electron gain enthalpy and electronegativity. The absence of d orbitals in a second period, of the presence of d and a d and f orbitals in a heavier element, that starting from the third period onwards and have significant effects on the properties of the element. In addition, the presence of all these three types of element, the metal, metalloids and non-metals, that bring the diversification in the chemistry of these elements as well. That having learned the chemistry of the element of the groups 13 and 14 of the P block of the periodic table of class that we had done in your class 11th here, in the same cases you will have to learn the chemistry of the elements of the subsequent group in this unit here. On the same behalf of it, we'll go ahead and that we'll have to first discuss about it, which is the topic which we have to discuss is your group 15 element. So this comes under P block element. So first group we have is your group 15 element that we have to discuss here. Let's go ahead. In terms of group 15 elements here, group 15 includes nitrogen, phosphorus, arsenic, antimony and bismuth. As we go down the group, there is a shift from that non-metallic to the metallic through metalloid character. Nitrogen and phosphorus are non-metals, and arsenic and antimony are metalloids, and bismuth is a typical metal here. Okay, these were on that same cases. So what occurrence that they, how they occurred, we'll talk about for the occurrence as well, how they the 15 group elements are occurring here. On the same cases, the molecular nitrogen comprises 78% by volume at the temperature in an earth crust. It occurs as sodium nitrate, which is NaNO3. That is called a child salt of beta as well. And the potassium nitrate, which is known as Indian salt petre. It is found in the form of the proteins in plants and animals. Therefore, phosphorus that occurs in minerals of the apatite that we have here. And in the same cases for the apatite family, which is a Ca2 that we have here, that is your Ca9 and PO4 whole 6, and then CaX2, which is X is your fluorine, chlorine or OH. Example like fluoropatite, which is Ca9 PO4 6 dot CaF2 as well, that we have to discuss here. Onto the same cases we have to talk about it, which is .CaF2, and which are the main components of the phosphate rocks here. Phosphorus is an essential constituent of animals and plants matter that we talk about it. So we are on the same cases that we have to talk about it, and on the same cases that the phosphorus is essential constituent of animal and plant matter, and it is present on the bones as well as for the living cell. And phosphorus that protein that are present in milk and eggs, and arsenic, antimony and bismuth are found mainly on sulfide minerals. That the important atomic physical properties in the group elements, that we'll talk about it with the atomic and physical the properties of the group 15 elements here. So we'll go ahead first, and that, as I told you, and let's go ahead with the property to discuss here. So first we'll talk about it, which is about that we have to discuss here on the same cases. And that we have your first, we have your discuss about property, then we have your nitrogen, phosphorus, sp, and of course your bismuth, okay, antimony, bismuth. Then we have on the same cases for the property, the first property we'll talk about is your atomic number. Okay, the second property we talk about it, which is atomic mass. The third property we talk about is the electronic configuration. We'll talk about these. The fourth we talk about ionization enthalpy here. With the same case, we'll talk about the electronic configuration. After that, we'll talk about the delta R of H here, and that we have the value for that as well. The delta of H by kg, that we talk about kg mole inverse here. We'll find for that as well. For the first value for the electronic configuration, we'll talk about it. After electronic configuration, we have here, this will be the ionization enthalpy. Okay. This is first, second, third ionization enthalpy. Then after that we'll talk about your electronegativity. Then we have covalent radius. Then ionic radius. Per ppm. Melting point per Kelvin, boiling point per Kelvin, then density per gram centimeter inverse cube with at 298 Kelvin here, that we have to talk about it. For the same we'll talk about here as well the value for all these. And that is for bismuth here. Okay, this has been SV. So on the same behalf of it, we'll talk about it, and that is on the same field, atomic number for N we have here is your 7, P is 15, arsenic is 33, 51, 83. Atomic mass we have 14.001, 30.97, 74.92, 121.75, 208.98. Another we have for the electronic configuration for the nitrogen we have is your H2S2 then for any 3S2 3P3, argon 3D10 4S2 4P2, then Kr 4D10 5S2 and 5P that 3. Then for this we have xenon 4F14 5D10 and 6S2 6P3 that we have. Then for the ionization enthalpy, 1 for the nitrogen we have is 1402, 1012, 947, 834 and 703. Ionization enthalpy for the second is 2856, 1903, 1798, 1595 and 1610. The third we have is 4577, 2910, 2736, 2443 and 2466 as well. For the electronegativity we have here is your 3.0, 2.1, 2.0, 1.9 and 1.9. For the covalent radius we have this is 70, 110, 121, 141, 148 here. Another we have here is 171B, 212B, 222B, 76C and 103C. The another we have is 63 abstract, 317D, 1089D, E and 904, 544. The another we have 77.2 abstract, 554 B, 888F, 1860, 1837. The another we have is your density here, which is 0.879. That is we have G 1.823, 5.778H, 6.697 and 9.808 here that we have to talk about it. So in the same case for the E power that we have here third, that is a single bond which is E element, and E power 3 minus and E power 3 plus D, that is a white phosphorus, a gray alpha form in 3.838.16 and some sublimation temperature we have at 63 Kelvin, and a gray alpha form which is molecular N2. So trends of some atomic, physical and chemical properties of the group that we'll discuss here. First we'll discuss about electronic configuration here as well. So first we'll talk about it. This is terms of electronic configuration here. In terms of electronic configuration, the valence shells electronic configuration of these elements is NH2, NP3, and that the s orbital that we have in these elements is completely filled, and the p orbitals are half filled, that making their electronic configuration extra stable, that we have talked about it. The another we have atomic and ionic radii. First is your, that is we had discussed about it, which is occurrence. Then we had discussed about electronic configuration. The third we have is your atomic and ionic radii. In terms of that, that the covalent and ionic in a particular state, that the radii increases in the size that the state down in the group here, and on the same cases we have to talk about it. There is a considerable increase in covalent radii from N to P, that is from nitrogen to phosphorus, and however from arsenic, arsenium and that is your bismuth, we talk about it. For the arsenic to bismuth, that only a small increase of the covalent radius is observed, and this is due to the presence of completely filled DNS block here, orbitals to the heavier orbital members as well. We'll talk about the fourth category, which is ionization enthalpy. Fourth is ionization enthalpy. In terms of ionization enthalpy, the ionization enthalpy decreases down the group due to the gradual increase in atomic size because of the extra stable half-filled p orbital electronic configuration and smaller size, that the ionization enthalpy of the group 15 element is much greater than that of the group 14 element in the corresponding period. The order of the successive ionization enthalpy we have, that is delta H1 is less than delta H2 is less than delta H3 here. The next fifth we'll talk about is electronegativity that we have to discuss here. Here we go ahead with another one. This is the fifth one we'll have to talk about it, which is after the ionization enthalpy, and that is the electronegativity. In terms of electronegativity, the electronegativity value, where in general that decreases down the group with the increasing atomic size, and however amongst the heavier element the difference is not that much pronounced as well. We'll talk about the another one, which is physical properties. In terms of physical properties, here all the elements of these groups are polyatomic, and dinitrogen is a diatomic gas we have, while all other are solids. And metallic character increases with down the group, and nitrogen and phosphorus are non-metals. Arsenic and antimony malloids, and bismuth is a metal. This is due to the increase in ionization enthalpy and the increase in atomic size. The boiling point here, where the boiling point in general that increases from top to bottom and the group in the group, but the melting point increases up to the arsenic and then decreases up to bismuth. So except nitrogen, all the elements shows allotropy as well. We'll talk about the seventh characteristics that the seventh we have to talk about the group 15 elements that we have here, as that is the chemical properties. In terms of chemical properties here, there the oxidation states and trends in the chemical reactivity we talk about it, where that the common oxidation state of these elements are -3, +3 and +5. So the tendency to exhibits -3 exhibition oxidation state that decreases down the group due to increase in size and metallic character. In fact, that the members of the group bismuth that hardly forms any compounds in -3 oxidation state, where the stability of that +5 oxidation state decreases down the group, and the only well characterized by that is your BiB, that compound is BiF5. In the same case, the stability of the +5 oxidation state that decrease on that of the +3 state increases, and due to the inert pair effect down the group, and that the nitrogen exhibit +1, +2, +4 oxidation state also when it reacts with oxygen, and phosphorus also shows +1 and +4 oxidation state in some that we have oxo acids as well. In the case of the nitrogen, all the oxidation state from +1 to +4 that tends to the di-proportionate in acid solutions. For example, 3HNO2 that will give you HNO3 plus H2O plus 2NO as well. Then we have similarly in the case of the phosphorus, nearly all intermediate oxidation state that is disproportionate into +5 and -5 both in alkali and acid as well. However, +3 oxidation state in case of arsenic, antimony and bismuth that becomes increasingly stable with respect to the disproportionate proportions as well. The nitrogen is restricted to a maximum covalency of 4, that since only 4 1s and 3p orbitals are available for bonding, and the heavier elements have vacant d orbitals and in outermost shell that which can be used for the bonding covalency, and hence expand their covalence as in pf6 as well. In the anomalous property of nitrogen, if I am going ahead for this, that is we had done the that is will be in the form of In the same case for the anomalous property of nitrogen here, where nitrogen that differs from the rest of the members of this group that due to its small size as well, and high electronegativity, high ionization enthalpy, and high non-availability of the orbital, and nitrogen have a unique ability to form p-pi or p-pi multi-bonds with itself and with other element, have small size and high electronegativity as well. Example is carbon and oxygen, where heavier elements of this group do not form p-pi and p-pi bond as their atomic orbitals, and that are so large and diffuse that they cannot be have effective overlapping. Thus, nitrogen exists as a diatomic molecule with a triple bond 1s and 2p, so between the two atoms. Consequently, its bond enthalpy 941.4 kg that kilojoule mole inverse is very high. On the contrary, that the phosphorus, arsenic, and antimony that form a single bond as that is as ASAS, or you can say SBSB, so the single bond, while bismuth forms metallic bond in an elemental state. And however, that the single NN bond that we have is a weaker than of the simple single PP bond. With the same, because of the high inter-electronic repulsions of the non-bonding electrons, and owing to the small bond length, and as a result, that the catenation tendency is weaker in that nitrogen, and in the same cases for the respect towards nitrogen. And another factor which affects that the chemistry of the nitrogen is the absence of orbital and in its valence shells as well, and besides the restricting its covalency in 4 nitrogen that cannot form that is the d pi or pa pi bond as the heavier element that can be example of R3p double bond O or R3p double bond CH3. So where R is your alkyl group here, and on the same cases that the phosphorus and arsenic that can also form that is your d pi and d pi bond as well. And also with the transition metal, which they form the compound of PC2H5 whole thrice, and As or C6H5 whole thrice act as ligands as well. In the same case for the reactivity towards that is hydrogen, we have to talk about it, where all the elements of the group 15 form that hydrides of the type EH3, whose E is equals to that is your nitrogen, phosphorus, arsenic, and your SB, and then by that your we have and bismuth. Some of the properties of these hydroids are that we'll discuss here in the further. And before starting with that, the hydroids that shows the regular gradations on the properties, that the stability of the hydroids that decreases from the NH3 to BiH3, and which can be observed from this bonding dissociation enthalpy. Consequently, that the reducing character of the hydrides that increases ammonia in only a mild, that is reducing agent, and while your BiH3 that is the strongest reducing agent amongst all the hydrides, and basicity also decreases in the order as well. That we will talk about it, which is we have as follows, like NH3 is greater than pH 3 is greater than ASH3 greater than SVH3, and which is greater than equals to BiH3 here that we have. So now we'll talk about it in the same cases. We'll discuss about the properties of hydrides of group 15 element that we have to discuss here, which is in the terms of properties. We'll talk about NH3, PH3, SH3, SBH3, and BiH3. So on the same behalf of it, we'll make it a table here. So we'll discuss here, that is your property for NH3, PH3, ASH3, SBH3, and BiH3. So that we have that we'll talk about it here. So on the property with the taking, the first property we'll talk about it is the melting, that is melting point. per Kelvin, boiling point per Kelvin, E minus that H bond, that is your distance, PM, HEH, that we have your angle, that the F of H bond have kJ mole, the inverse, and then of course we have your delta H enthalpy, we have E minus H by kg that we have here. Okay, on the same cases we'll talk about it. So here we go ahead. So here that is for NH3 here. This is we have your 19.5 195.2, and this is 139.5, 156.7, 155, and this is no. For the boiling point is 238.5, it is 185.5, 210.6, 254.6, and 290 as well. The another we have here is 101.7 here, 141.9 as well, and then we have your which is 151.9 and 170.7, and then we have for the angle we have is 107.8, 93.6, and 91.8, 91.3 that we have. This is minus 46.1, 13.4, 66.4, 145.1, and of course 278 here. Then for this we have 389, 322, 297, 255, and this is so on. Now we'll go ahead further, which will discuss about the reactivity that towards the oxygen we have to find out, and that is also an important one. And as I told you very well in the starting, that we have to cover up many more things to be discussed here, and it should totally depend upon the duration, that how we exceed, how much we can exceed that. On the same behalf of it, we will be going to discuss here in the detail as well, and that we have to go ahead. On the same cases, these all are things that these were all topics that we are dealing with is all always important, and that we even have to talk about it. So on the same case, now we will be going ahead, and that the table has been completed. Now we will be going ahead to discuss about the another topic, that is in terms of that is reactivity towards oxygen. We'll talk about here. To the same way, we'll talk about the second one here. This is reactivity towards the hydrogen we are talking about. So for that is the first part of the chemical that we are talking about. The second we'll talk about reactivity towards the oxygen, that all these elements from two types of oxide, which is E2O3 and E2O5, that the oxide of the higher oxidation state, that of the element is more acidic than that of the lower oxidation state. Their acidic character decreases down the group, and the oxides of the type E2O3 of the nitrogen and phosphorus are purely acidity, that is your acidic, and that of the arsenic and antimony amphoteric, and those of the bismuth, that of the arsenic and antimony, and that of bismuth predominantly basic as well. We'll discuss about another one, which is reactivity towards halogens, that these elements react to form two series of halides, which is EX3 and EX5. On the same case, the nitrogen does not form the pentahalides due to the non-availability of the orbitals in the valence shell. The pentahalides are more covalent than the trihalides, and all the trihalides of these elements except those of nitrogen are stable. In case of the nitrogen, only Na3 is known as to be stable, and where trihalide except BiF3 are predominantly covalent in nature as well. Where in terms of reactivity towards metals, yeah, all these elements that react with metals to form their binary compounds exhibiting -3 oxidation states such as Ca3N2, which is calcium nitrate, and nitride, Ca3P2, which is calcium phosphide, Na3As2 sodium arsenate, and Zn3Sb2, which is zinc antimonide, and Mg3Bl2, which is magnesium bismuthide as well. We'll go ahead with the further one, which we'll discuss about the question here. That even though we have to discuss the question, we have this is the first question of this particular unit that we have to discuss here, which is to be as follows, and that we have to go ahead. So the question is, though nitrogen exhibits +5 oxidation state, it does not form pentahalides. If reason here. So here we go ahead and that we have to discuss about it. So though nitrogen, that we have to give an example. So first I will write it down the question here, then we'll go ahead for the solution for this as well. So the question is, though nitrogen exhibits +5 oxidation state, it does not form pentahalides. Give reason. In terms of it, where nitrogen with N equals to 2 has S and P orbital only, it does not have D orbital to expand the covalence beyond 4. So that is why it does not form pentahalides as well. We'll talk about another question, that is the second question here, which is that is your pH3 has lower boiling point than NH3. Why? That you have to explain. pH3 has lower boiling point than NH3. Why? So we have to explain it. So on the same here, for that, unlike NH3, pH3 molecules are not associated through hydrogen bonding in a liquid state. That is why the boiling point of pH3 is lower than NH3 here. Now we'll be having another question that you have to solve by your side, and that is also an important one, as I told you. That is, why are pentahalides more covalent than trihalides? That you have to talk about it. And the another we have is your why is BiH3 the strongest reducing agent amongst all the halides of group 15 elements here. Now we'll talk about another topic which we have to discuss about it, and that is also an important one, which is about dinitrogen. Let's go ahead to discuss about dinitrogen, where we'll discuss about the preparation as well as for the properties as well on the same behalf of it, and for the reaction also we have to do it for the thermal decomposition, that we have to go ahead for the sodium and sodium azide. So that we'll do it here only. So I will just go ahead, write the reaction of thermal decomposition of sodium azide, and that is for the thermal decomposition of sodium azide that give dinitrogen gas. And for that you can just represent it like in the form of was in the like form of will give is 2Na, and 3 will give 2Na plus 3N2. So here the question they can ask you is, why is N2 less reactive at room temperature? So of course N2 have a 3 triple bond sharing, so that's the reason. You can just go ahead. Now in the same case we will discuss about dinitrogen, as I told you. So let's go ahead to discuss that as first. In terms of dinitrogen we have to talk about it. So dinitrogen जो होता है, that we have to go ahead in detail, but dinitrogen में सबसे पहले we'll go ahead for the preparation. So in terms of preparations here, dinitrogen is produced commercially by the liquefaction and fractional distillations of air liquid dinitrogen, which is at the boiling point we have 72.2 Kelvin, that distills out first, on the leaving behind liquid oxygen, which is the boiling point we have 90 Kelvin. In the laboratory, the nitrogen is prepared by treating in aqueous solutions of ammonium chloride with sodium nitrate, and for that same case we have an equation as well that we have here. It will be as follows: NH4Cl, that is aqueous, we have, plus NaNO2, which is aqueous, and that will give N2, which you see we have a gas, plus 2H2O liquid, plus NaCl, which is in the form of aqueous, where small amounts of NO and HNO3 are also formed in this reaction, and these impurities can be removed by passing the gas through aqueous sulfuric acid containing potassium, that is dichromate, and it can be also obtained by the thermal decomposition of ammonium dichromate as well. So which is, you have HNH4 H4 Cr2O7. In the presence of heat, it will give N2 plus 4H2O plus Cr2O3, very pure nitrogen that can be obtained by the thermal decompositions of sodium or barium azide. So for the same case we have Ba N3 whole twice will give Ba plus 3N2 here. So that we have to talk about it, and the same here for the same cases we'll go ahead, that is, we'll talk about the properties. So dinitrogen is a colorless, odorless, and tasteless and non-iotoxic gas as well. Nitrogen atom has two stable isotopes, where we have a 14N and a 15N, and it is very low solubility in water, which is 23.2 centimeter cube per liter of water at 273 Kelvin and 1 bar pressure as well, and low freezing point and boiling point as well, where dinitrogen is rather inert at a room temperature because of the high bond enthalpy of and triple bond, that as I told you. Reactivity, however, increases rapidly with the rise in the temperature, and at the higher temperature it is directly combined with some metals to form predominantly ionic nitrides, and with the non-metals covalent nitrides, and a few typical reactions are. So on the same case it will be 2 and 6 Li plus N2 will give, in the presence of heat, it will give you 2 Li 3N that we have, and another we have is your 3Mg plus N2 in the presence of heat will give Mg3N2 here, that we have to talk about it. Now we'll go ahead further, which we'll talk about it, and even though which we have to discuss about here. It combines with the hydrogen at about 773 Kelvin in the presence of catalyst, which is your Haber's process to form ammonia, and on the same cases we have an equation that is N2 in the form of gas plus 3H2 gas will give, it will be 773 Kelvin, that is will give 2NH3 gas here. So in the same case, for that, the dinitrogen combines with a dioxygen only at a very high temperature at about 2000 Kelvin to form nitric oxide, that is NO. And on the same case we'll form it here, which is, it will be as follows: N2 plus O2 in the presence of heat give 2NO, which is your gas here. Now we'll talk about the uses of dinitrogen. On the same cases for the uses, if I'm going ahead, so in the same case for the uses, the main uses of dinitrogen is in the manufactures of ammonia and other industrial chemicals containing the dinitrogen. An example is a calcium cyanamide, and it also find a use where an inert atmosphere is required. Example, in iron and steel industry, inert diluent or for reactive chemicals. Liquid dinitrogen is also used for the refrigeration of preserved biological materials, food items, and in that is your cryosurgery as well. Now we'll discuss the another third atom that we have as your the element that we talk about, which is your ammonia here. For that also we'll discuss about the preparations and then of course properties as well, that is in the detail. So let's go ahead with ammonia here. We'll talk about another one which we have to discuss here, which is the ammonia here. In terms of ammonia here, that we'll talk about preparation. So ammonia is present in a small quantities in air and soil, where it is formed by the decay of nitrogenous organic matter, which is example is your urea. And this in case for the urea, we will be writing it out the equation here, and that is also an important one. So for that we have NH3, sorry NH2CO, NH2 plus 2 H2, NH4 2 CO3. It will give you 2 NH3 plus H2O plus CO2. On a small scale, ammonia is obtained from the ammonia salts while decomposes when treated with the caustic soda or lime. For that, we have equation here, which is 2NH4Cl plus CaOH twice will give 2NH3 plus OH2 plus CaCl2. For that, NH4 2 SO4 plus 2 NaOH, that will give 2 NH3 plus 2 H2 plus Na2SO4 here. On a large scale, ammonia is manufactured by the Haber's process, and that we have is your N2 gas plus 3H2 gas. It will give 2 NH3 gas here. And in accordance with the Le-Chartier's principle, the high pressure that would favor the formations of ammonia, the optimum conditions for the productions of ammonia are pressure of 200 into 10 to the power 5 Pascal, about the 200 atm, and temperatures of approximate 700 Kelvin, and the use of the catalysts such as iron oxide with small amount of K2O and Al2O3 to increase the rate of the attainment of equilibrium. With a flow chart for the productions of that is your ammonia, that is shown here, and earlier the iron was used as a catalyst with the molybdenum as a promoter as well. Now we'll go ahead further, which will discuss about how the liquid ammonia is being produced, and which are for the manufacturing of ammonia as well, that we'll discuss about it, where the compressor at 20 MPa. Then after that it will go to the catalyst iron oxide Al2O3 plus K2O, then it is formed it out, and then after that it is forming here. So this is what liquid nitrogen or liquid ammonia or ammonia will be formed here. On the same case for the property for the structure, that I'm going ahead for the ammonia here. So this is being H, this is being H, this is being H here, which is at 101.7 pm. This is the angle, we have 107.8 degree, and of course this is a lone pair here. So in the same case, this is for NH3 here. Ammonia is a colorless gas with a pungent odor, and its freezing and a boiling point are 198.4 and 239.7 Kelvin respectively. In the solid and the liquid state, it is associated through the hydrogen bond as in the case of the water, and that accounts for the higher melting boiling point than expected on the basis of the molecular masses, where the ammonia molecule is trigonal pyramidal with the nitrogen atom at the apex. It has 3 bonds pair and 1 lone pair of electron, that to be shown in the structure. Ammonia gas is highly soluble in water. Its aqueous solution is weakly basic due to the formations of OH minus ion. On the same case for that, we'll made it out. NH3 gas plus H2O liquid, it will give NH4 plus aqueous plus OH aqueous here. Then after that we'll talk about it, which is another one. It forms Ammonium salts with acid, example NH4Cl and NH4 twice SO4, etc. As a weak base, it precipitates the hydroxide, hydrated oxide in the case of the some metals of many metals from their salt solution. For example, that it forms here as your ZnSO4 aqueous plus 2NH3 NH4OH aqueous, it will give ZnOH twice S plus NH4 times SO4 aqueous. This is ZnOH here, that is your white ppt. In terms of it, that is the another we'll talk about it, which is FeCl3 aqueous plus NH4OH aqueous. It will give Fe2O3.XH2O solid plus NH4Cl aqueous. This is the Fe we have. This is your prawn ppt that is formed here. The pressure or balloon pair of electron on a nitrogen atom of the ammonia molecule that makes it a lowest base. It denotes the electron pair and forms linkage that with metal ions, and the formations of such complex compound finds application in detections of metal ions such as Cu2 plus and Ag plus as well. And for the same case, the reaction will form it, that is Cu2 plus aqueous plus 4NH3 aqueous. It will give CuNH3O4 2 plus as well, that is in aqueous here. The another we'll talk about it, which is your, this is in blue color, and this is with this is the deep blue. Now for the another question we have is your Ag plus, which is in aqueous, plus Cl minus aqueous. We give AgCl, that is salt. And same case for Ag, that is plus, we have your colorless. And for AgCl, that is your white ppt. The another we'll talk about it, that is your AgCl solid, that is plus 2NH3. This aqueous will give AgNH3 whole twice Cl aqueous. This is we have here is your colorless. This is white ppt. Yeah. On the same cases, when we are talking about ammonia more in detail, there are many more equations that we have to form here, and that is also, that is also important as well. On the same behalf of it, when we are going for the further one, which we have to talk about it, and even though which is also important one, in terms of copper as well, then we have Zn as a 4 as well, that they are forming here, and as we have presented as well, and for the copper as well. So these all plays an important role when we are further moving ahead to solve it out. In the same cases for that, the uses of ammonia, if I'm going ahead for the uses here, in terms of uses, that ammonia is used to produce the various nitrogenous fertilizers, ammonia nitrate as well. On the same cases, the urea, ammonia phosphate and ammonia sulfate as well, and in the manufacture of some inorganic nitrogen compound, and the most important one being the nitric acid, liquid ammonia is also used as a refrigerator as well. We'll talk about another question we have to talk about it, that is the fourth question of question, and that we have to go ahead here, which is the question number 4. The question is, why does NH3 act as a lowest base? So which we have to talk about it. Why does NH3 NH3 act as a Lewis base. This has been here for the nitrogen atom in NH3 has one lone pair of electron which is available for the donation, and therefore it acts as Lewis base. So you can just say that they have a lone pair one. Okay, that we have. So this is the reason why it is no, it will act as Lewis base here. And now we go ahead with another one which we have to talk about it in terms of here, and that is also an important one. So there are many more questions that we have to talk about it in detail. That is the question we have. Mention the conditions required to maximize the yield of ammonia and the reactivity dioxide, and how does ammonia react with a solution of CO2 plus. This we have to also talk about it. Now we'll go ahead with oxides of nitrogen, that we have to go ahead in a detail. Oxides of nitrogen, the oxide of nitrogen as well, the structures of oxides of nitrogen as well, that we have to talk about it. So before oxides of nitrogen, we will go ahead. In terms of oxides of nitrogen here, the nitrogen forms a number of oxides in a different oxidation state. Here the names and formula preparations and physical appearance of these oxides that we have, and we'll talk about the oxides of nitrogen here. In the same cases, we'll have to discuss about the name, formula, oxidation state of nitrogen, as well as the common method of preparation, physical appearance, and chemical nature as well. That even though we have to discuss about it. So let's go ahead for that, and that we will have to find out as well. We'll take it and we make it, a sort of, that is a table that we have to make it out here. So the name we'll talk about first. Then we have a formula. Then we have oxidation state of nitrogen. Then we have your common method of preparation. Then of course we have your that is your physical appearance and chemical nature. Okay, so we made it. So here we go ahead with the detail about it, which is we have dinitrogen oxide here. The first we have. And here that we can talk about, that is known as your nitrogen 1 oxide. So on the same behalf of it, the formula for that we have, we just represented first that, which is N2O. Oxidation state of nitrogen is +1. The common method of preparation we have is NH4 NO2 NO3, that is in the presence of heat. It is N2O plus 2H2O. And here that is the physical appearance and chemical nature. We have colorless gas, neutral. This is for the nitrogen oxide that we have, even though which we have to talk about it as well. On the same cases, we'll go ahead further, which we'll have to talk about it. That is the another one is on the same cases we have for the another one is your nitrogen monoxide. Which is nitrogen second oxide. NO, this is +2. So here that is 2NaNO2 plus 2FeSO4 plus 3H2SO4. That will give Fe2SO4 thrice plus 2NaHSO4 plus, that is your 2H2O plus 2NO here. So this has been the physical, that is your colorless gas and neutral. The another we'll talk about it, that is the third one we'll talk about, that is Dinitrogen Trioxide, and that is also important one. This is your nitrogen 3 oxide, and that is being representing here in the form which is N2O3 plus 3, this is 2NO plus N2O4. It will be at the 250 Kelvin. It will give 2N2O3. For that is Zoo solid acidic. So for the same case we'll go ahead here, that is the other one we'll talk about it, and which is also an important one here. So blue, that is your blue solid and acidic as well. The another we'll talk about it, which is your the nitrogen dioxide. Then nitrogen dioxide, which is your nitrogen 4 oxide. We have this is so for the same case we have here the formula we have is NO2, which is plus 4, and 2 PbNO3 whole twice. It will give 6 at 673 Kelvin. 4NO2 plus 2 PbO plus O2, which is brown gas or acidic. Now we'll go ahead for the another one which we'll talk about it, and that is the another one is dinitrogen tetroxide, and that is your nitrogen 4 oxide. The formula for this we have N2O4 and that is the valence we have plus 4, 2NO2. It's cool as well, and here this reverse process is your heat, so that will give N2O4. This is your colorless solid or liquid and acidic. Now we'll talk about the another one, and that is of course the last one we'll talk about here as well, and which is also an important one here, and that is the another one we have here is your nitrogen dinitrogen pentoxide, which is your nitrogen 5 oxide here. And for the formula we have here is N2O5. This is the oxidation state of nitrogen. We have plus 5. Equation is 4HNO3 plus P4O10 will give 4HPO3 plus 2N2O5. Colorless solid or acidic. Colorless solid and acidic here, that we have to find out. So here we'll end it up here only, because it will be exceeding more an hour, so it will surely complete in this next coming class. So here we'll end up it. First of all, it's a huge request from my side to all the viewers to please go through with the subscribe button, and please like, share and subscribe to our channel, so that many maximum people can get the information at once, and even you can also enjoy the video as well. If I'm talking about the other than chemistry, we are dealing with the verbal reasoning, where we had been divided into two parts, which is verbal reasoning and non-verbal reasoning. Verbal reasoning we had completed, that is your the general mental ability and the logic reasoning, and in the non-verbal reasoning we had started with, which we had completed series, analogy, classification, analytical reasoning, mirror image, water image, embedded figure, figure matrix, and conditions of incomplete pattern as well. Other than that, we are dealing with the quantitative aptitude, where we had started with arithmetical ability, where we have to cover up, that is the operations on number, LCM and SCF of numbers, decimal fraction, simplification, square root and cube roots, and averages that we even have completed. In the next coming class, we'll have to start with another new topic as well. On the same case, we had completed a sociology and software engineering. Therefore, you can go ahead with the playlist. You will find out each and every video there as well. Other than that, we had completed in terms of chemistry. Coming towards this has been important for the academic as well as for the competition here. On the same behalf of it, if I'm going ahead here in the detail, that is your unit 1, that is your solid state. We had completed general characteristic of solid state, amorphous and crystalline solid, classification of crystalline solid, crystal lattice and unit cell, number of atoms in the unit cell, number of atoms in unit cell, closed pack structure, packing efficiency, calculation involving unit cell dimension, imperfections in solid, electrical properties, magnetic properties as well. Unit 2 is your solution, that we had covered up types of solution expressing concentration of solution, solubility, air pressure of solid liquid solution, ideal and non-ideal solution, colligative property of the determination of molar masses and nominal molar masses as well. Unit 3 is your electrochemistry, which we have to cover up is your electrochemical cell, galvanic cell, Nast equation, conductance of electrolytic cell solution, electrolytic cells and electrolysis, batteries, fuel cells and corrosion. Unit 4 is your chemical kinetics, which we had cover up your rate of chemical reaction, factor influencing of rate of reaction, integrated rate equation, pseudo first order reaction, temperature dependence of the rate of the reaction, collision theory of the chemical reaction as well. Unit 5, which we had completed your surface chemistry, where we had completed adsorption, catalyst, collides, classification around us, classification of collide, emulsion, collide around, so that we had completed. Unit 6 we had completed, that is your general principles and process of isolation of element, where we had completed the occurrence of metal, concentrations of ores, extractions of crude metal from concentrated ore, thermodynamic principle of metallurgy, electrochemical principles of metallurgy, oxidation, reduction, refining, uses of aluminium, copper, zinc and iron. The unit 7 which we had started with, which is the P block element, where we had completed group 15 element, dinitrogen, ammonia, and oxides of nitrogen we had started with. Nitric acid we had to complete it, phosphorus, allotropic forms, phosphine, phosphorus halides, also acids of phosphorus, group 16 element, dinitrogen, simple oxide, ozone, sulfur, allotropic forms, sulfur dinitrogen, oxo acids of sulfur, sulfuric acid, group 17 element, then chlorine, after that the hydrogen, chlorine, chloride, oxo acids of halogens, interhalogen compound, and group 18 elements as well, that we have to discuss here. After that, we have to start with the unit 8, which is the D and F block element, where we have to discuss positions in the periodic table, electronic configuration of the D block element, general properties of the transition element of the D block, some important compounds of transition element, the lanthanide, actinide, some application of D and F block element as well. Unit 9 is your coordination compound, that we have to cover up, where we have to cover up the oneness theory of the coordination compound, definition of some important terms pertaining to the coordination compound, nomenclature of the coordination compound, isomerism in the coordination compound, bonding in the coordination compound, bonding in metal carbon analysis, stability of the coordination compound, importance and application of coordination compound here. So here we'll be ending it up, and it's a huge request from my side to all the viewers to please go through with the subscribe button, and please like, share and subscribe to our channel, so that many and maximum people can get the information at once, and even you can also enjoy the video as well. Thank you. Hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion or a comment box here. Thank you.